Hello, and welcome back to the channel where we explore everything and beyond. In this video, we're continuing the journey of building a new web client for Tryton. Today, we're focusing on the UI components. Since I chose PrimeVue as the UI library for this experiment, the next logical step is to map Tryton's view definitions to PrimeVue-based components. As mentioned previously, the initial scope of this project centers on two core view types, the form view and the tree view. Before implementing anything, it's important to understand what the client is expected to render. Tryton provides schemas in its source code that define the structure and available elements for each view type. Reviewing these schemas gives a clear picture of what the web client needs to support. Let's begin with the form view. In the form view, UI elements can be grouped into two categories, containers and non-containers. Containers are structural elements. They organize layout and define how other elements are arranged. These include groups, notebooks, and the form element itself. Non-containers are the actual UI elements displayed within those structures. These include labels, fields, images, separators, new lines, buttons, and links. Fields require special attention because they represent data, and there are many different types. In the client, fields are rendered using widgets. Each widget corresponds to a particular way of rendering and interacting with a field. When mapping these elements to PrimeVue, the relationship is not one-to-one. Instead of directly assigning a PrimeVue component to each Tryton element, I created a layer of view components that wrap and compose PrimeVue components internally. This provides a level of abstraction between the Tryton schema and the UI library. The only exception is the label element, which is implemented using the standard HTML label element. For naming consistency, I refer to all form-related UI elements as widgets. For example, label becomes label widget, separator becomes separator widget, and so on. Fields are implemented as dedicated components such as char field, Boolean field, and others depending on the type. The general pattern is consistent across the form view. Each Tryton element corresponds to a view component, and that component internally composes PrimeVue elements as needed. This approach keeps the mapping explicit and makes it easier to adjust behavior at the component level. For instance, the label widget applies styling based on the associated field state. In this implementation, required fields are styled differently. The styling logic lives within the widget, so it remains close to the rendering logic. The newline widget is a simpler example. It is an invisible element whose only responsibility is to instruct the parent grid layout to move to a new row. Even though it has no visual output, it still plays a structural role in layout composition. Fields are handled through a dynamic component called field widget. Rather than hard-coding a specific field type, this component determines which concrete field component to render based on the field definition. A char field renders a char field component. A Boolean field renders a Boolean field. The same pattern applies to other types. The char field component follows the same structural approach as other widgets. It is responsible for rendering the input element and displaying validation messages when necessary. The validation logic itself is handled elsewhere in the application. This keeps validation rules separate from presentation logic. Most other field components follow the same pattern. More complex field types, such as selection fields or relational fields, introduce additional responsibilities like option handling or related record selection. These will be covered in a later video, since they involve additional features beyond basic rendering. Now, let's move on to the tree view. The overall approach is similar in principle, but different in responsibility. Instead of rendering full interactive forms, the tree view presents structured data in tabular form. For this view, I created a column widget component that is used exclusively within the tree view. Like field widget, it is dynamic. Each field type has a corresponding column component responsible for rendering its value. At this stage of the project, the components for the form view and tree view are implemented separately. This means that even if a field type exists in both contexts, it has different components depending on where it is used. While this may introduce some duplication, it keeps behavior clearly scoped to each view type and simplifies early-stage development. In this implementation, tree views are currently read-only. As a result, column components focus on formatting and presentation rather than editing or validation. For example, the date column component corresponds to the date field type. Its primary responsibility is formatting the value for display. Date formatting and processing are handled using Luxon, which simplifies working with date-related transformations. Other column components follow a similar structure: receive a value, apply formatting if necessary, and render it appropriately within the table. Filtering is another aspect of the tree view. The official web client provides text-based filtering using domain expressions, where users manually enter filter conditions. In this implementation, an alternative interface is explored. Two components are introduced: a filter builder component and a search component. The filter builder provides a structured way to compose conditions through a visual interface. The search component supports quick input-based filtering. Both components are included to demonstrate different approaches to filtering within the same view. They serve different interaction styles while operating on the same underlying data. Filtering also uses a dynamic component called search field widget. Similar to field widget and column widget, the render component depends on the field type. For example, a char field is handled by a char search field component. Across form, tree, and search contexts, the same field type behaves differently. In the form view, the component supports editing and validation. In the tree view, it focuses on formatted display. In the search context, it is editable but does not perform validation. This separation of responsibilities makes the behavior of each component explicit within its context. At this stage, clarity and isolation are prioritized so that each view type can evolve independently. That concludes this overview of the UI component implementation for the form and tree views. If you'd like to follow the progress of this project, consider subscribing to the channel. Feel free to like and share this video with anyone who might find it useful. Thank you for watching.